So the first thing to notice about this version of the HR diagram is that it's still got surface temperature decreasing as you go to the right along the y-axis, and it's still got brightness increasing as you go up. What's different about this HR diagram is that it has the colors called out, and remember the colors are connected to temperature, and it also has real star names called out. For example, not all stars, but just a few that we might know or we could get familiar with. The other thing this diagram has is it's really drawn some lines, and the lines are a little bit kind of arbitrary, but they are trying to separate out where the supergiants are. For instance, up here, where the giants are, where the main sequence of stars is here, and then where the white dwarfs are. So let's answer these questions that we've got. First question, which main sequence star in this diagram has the highest temperature? So remember, temperature increases as you go to the left, and we're looking for stars that are in this boundary here that's just called the main sequence. So I would say the main star sequence is something called Zeta Eridani, which is a super cool name. You can probably Google and find out a lot more about that star, but I say that star because it's the farthest to the left and it's within this main sequence boundary. Which type or group of stars in this diagram has the brightest stars? So remember, brightness is along the y-axis over here on the left, and so the brightest stars tend to be up here, near the top of the diagram. And really the winner is supergiants. They has all the stars that are the brightest. Doesn't matter what color they are, they're definitely the brightest. So let's put that one down, supergiants. What's the name of the brightest red supergiant with a temperature of approximately 3000 K? So, here's red. Remember, these are the colors. And by giving us red and the temperature, kind of redundant, right? There's no red stars that aren't somewhere around 3000 degrees. As soon as you get a little hotter than 3000 degrees, you're red-orange. And if you get a little hotter than 5000 degrees, you're yellow. So, I suppose you'll forgive us for being a little redundant here, but the brightest red supergiant looks like Betelgeuse. That's another great name, Betelgeuse. And I say that because it's here near the top in the red color category. Color categories are vertical. Stages of stars are these dotted lines. Next, describe our sun. So here's our sun right here. I should probably highlight it so you can see it. Give me a sec here. So if I click to draw, and if I click the highlighter, I'm going to use yellow, of course, because it's our sun, right? So here's our sun right here. Notice that our sun is, well, somewhere between 5,000 and 6,000 degrees. Maybe it's 5,500. And the brightness of our sun, well, the brightness of our sun on a scale that's defined by our sun is 1. It's as bright as itself, but it's in the type or group called the main sequence, and its color is yellow. So let's type that information in. The color is yellow. The type or group is its main sequence star. And the approximate temperature is 5,500 K. And now let's talk about which star is the least bright. And, well, we have a yellow star that's very low here on brightness, but it's yellow. And we asked for the white star that's least bright. So you would have to look over here at Sirius B, which is in the white dwarfs, it's true. and is fairly dim, and yet it is the white color. So let's put in Sirius B for this question right here. And so those are the questions here for question number 6, looking at this version of a HR diagram.